Professor Swati Madam, Professor H.K. Nigam. The external examiner Swati Madam is the VC in the Omega. Bhikkhu Bhai, father of Hardeep, Khachar. And all, thank you for joining with us. And usually this is the PhD Viva examination of Hardeep. And sir, usually the external examiners are supposed to be the chair this session.
Yeah.
Okay, so before you tell us, I want to give the brief introduction of our eminent external examiner, Professor H.K. Nigam, former head of the mathematics department, former dean of the mathematics, statistics and computer science, Central University of South Bihar, Gaya. Field of specialization is Fourier analysis, approximation theory, wavelet, compressive sensing. Sir has published more than 70 research papers, 2 books, and completed so many projects, so many invited talks. Sir is reviewer for more than 40 journals of AMS USA, ZMS Germany, and in very several journals. PhD supervisor, 7 students have already awarded the PhD degree under his guidance. 4 are doing the research, and his external examinations in various committee and various board of study. Sir, I would like to welcome the department and requesting you to please.
Yeah, I think it will already start the presentation. Yeah.
Good morning to one of our present here. So I, Hardeep Khachar, am going to bring my PhD defense bios presentation on study of rational Fourier series under the guidance of Professor Sayajirao. So this is the basic outline of the presentation, and so the classical Fourier series is generalized to various orthogonal series like Legendre, Vos, Chebyshev, Haar, and many more to provide flexibility in approaching different type of functions. Like a convergence property, numerical efficiency, and applications in various fields like engineering, mathematics, and physics. So the choice of orthogonal system depends on the specific problems and required accuracy. The classical Fourier series is not efficient enough to approximate non-periodic functions with discontinuities or singularities. To overcome such limitations, rational Fourier series is more suitable. So with the appropriate selection of parameters, this is the important part, selection of parameters. Yes. So, with the appropriate selection of parameters, the rational Fourier series exhibits faster convergence and better accuracy compared to classical Fourier series. So, besides theoretical applications, the rational Fourier series finds theoretical applications in fields such as control theory, system identification, signal processing, denoising, and many more. It should be noted that the computation of rational Fourier series can be more complex and computationally intensive as compared to Fourier series. So in 1920s, the rational orthogonal system was independently defined by Malmquist and Takenaka. So the orthogonal system is also called Malmquist-Takenaka system. The rational orthogonal system is defined as in this equation 1, where here alpha n is a complex sequence such that alpha k's are an open unit list D. It was observed that the system in 1 is complete in L2 if and only if the series 1 minus mod alpha k diverges. The simplest way to satisfy the previous condition is to assume condition 2. So in this
R here?
so here R is any for any like supremum of alpha k, and it should be any R, like we have to take R, whatever the supremum is, and it should be less than 1.
No.
So basically we are taking the term less than 1, and the alphas are bounded by R.
When you take the open disk,
Yes.
then closure is not required?
Yes sir, here we are not considering the closure part. So in the sequel, we will assume that condition 2 holds, and this is z star is z minus 0, t is 0 to 2 pi, and phi is a real sequence of that phi of 1 is greater than equal to 2, and phi increasingly tends to infinity as n tends to infinity. So in 1956, the concept of rational Fourier series with orthogonal system as rational orthogonal system was introduced by Zerbeshev. Analogous to Dirichlet kernel, in Fourier analysis, some property rational Fourier series are studied, and these results are related to pointwise convergence of rational Fourier series under the assumption of condition 2 where true. So if we take 2 pi periodic integrable function, then rational Fourier series of f is defined as in equation 3, where f at n is nth rational Fourier coefficient of f given by this equation 4. So if we take alpha k is equal to 0, then our series become Fourier series of f. And let alpha k equal to mod alpha k e raised to ix k. Then phi n e raised to ix k, ix becomes rho n x into e raised to theta n x, where rho n x is given as in equation 5 and theta n s is given as in equation 6. Here theta n x is a differentiable and strictly increasing function on 0 to 2 pi. Note that there are certain properties which differs from classical Fourier series. So if we take f and g as two integrable function of t bar, then convolution product of f and g is defined as in equation 7. So in Fourier coefficient we know that Cn f star g is Cnf into Cn g, where Cn represents Fourier coefficients. But this inequality does not hold for rational Fourier coefficients. So if we take fx equal to jx equal to sin x and equal to 1 and alpha 1 equal to half, then we get f at 1 j at 1 equal to minus root 3 by 4 and f star j at 1 is minus root 3 by 8.
Convolution is not satisfied.
Yes,
Yeah?
sir. Convolution property is
So
not.
other than convolution, any other property which does not fulfill?
Sir, as well, yes, like there are no results in absolute convergence for rational Fourier series as of yet. So
No,
I haven't
there-
seen
there are some
because
other
due to
properties.
this property we are unable to do.
There are some other properties also which does not hold for rational Fourier series.
There
Apart
are
from convolution.
there are some properties which hold for rational Fourier series, but the inequality would be different for the rational Fourier series as compared to. We will be discussing those.
Any property?
Is the definition okay? 7 double integral?
So it's
Integral over T2?
So yeah, any convolution.
Yes,
FT
yes. Yes, sir. There are certain properties which will look like they will differ from classical Fourier series, like order and all those that we will be looking in the next slides. So the pursuit of elegance and generality by mathematicians in reducing various properties have led to various extensions of concept of bounded variations. Some of the generalized bounded variations are due to Wiener, Waterman, Theta, Yoneda, Ecobax and many more. Properties of Fourier series of functions with these generalized variations such as order of Fourier coefficients, estimates of R systems have been proved for classical Fourier series and have been extended for double and multiple Fourier series. The concept of generalized variations, bounded variation has been also developed for single and double sequences and is usefully related to the trigonometric and double trigonometric results. So in this presentation we will take analogous results for rational Fourier series and rational trigonometric series of 1 and several values. So in 2013, the following properties of rational Fourier coefficient was obtained. If f is integrable, then f at n satisfies the inequality 8, where omega 1 f delta is supremum of integration 0 to 2 pi mod of f of x plus h minus fx dx, where 0 is less than h less than 2 delta. So this can be considered as Riemann-Leibniz lemma for rational Fourier series. If we take n tends to infinity, this term would tend to 0 as well as omega 1 would tend to 0. So we will get f at n tends to 0.
Omega 1 is modulus of continuity.
Yes, sir. Modulus.
Integral
Modulus.
modulus.
So in 1937, Young generalized the notion of phi-bounded variation of order of p and introduced the concept of phi-bounded variation. And in 1976, Waterman defined lambda bounded variation. So in Scrabble and Waterman in 1982 assimilated the ideas of Young's phi variation and Waterman's lambda variation. So a function f defined on an interval I is said to be a phi lambda bounded variation if this variation is finite. Where again phi is a continuous function defined on 0 to infinity, which is strictly increasing from 0 to infinity. Lambda equal to lambda n is a non-decreasing sequence of positive numbers such that summation 1 upon lambda n diverges. There is a finite collection of non-overlapping subintervals in AB. F of I is f of B minus f of A. So note that if we take lambda equal to constant sequence 1, then we get phi lambda BB reduces to phi BB, Young's variation. If we take phi x equal to x raised to p, then it reduces to lambda BB, which was given by C bar. And if we take phi x equal to x, then phi lambda BB reduces to Waterman's variation, lambda BB. And similarly, if we take phi x equal to x and lambda equal to constant sequence 1, then we get phi lambda BB reduces to the classical variation due to Jordan. So in the above definition of phi lambda bounded variation, it is typical to impose condition that phi is n function, which we will consider from here onwards. So a function f phi defined on 0 to infinity is said to be n function if these three properties are satisfied. number 1 phi of 0 is 0, number 2 phi is convex, number 3 phi x by x tends to 0 plus as x tends to 0 plus, and phi x by x tends to infinity as x tends to infinity. So the first condition ensures that zero length interval contributes nothing to the duration. The second condition ensures that there are functions in BBAB which are also in phi lambda BB. And the last condition ensures that there are functions in phi lambda BB which are not in BB. So also if phi is n function, then in view of every Davis result, phi is strictly increasing, non-negative and continuous function of 0 to infinity. One another condition usually imposed with the function in class of phi lambda bounded relation is delta 2 condition. So that the space becomes linear space. Function phi is said to have a delta 2 condition if there exists a constant b greater than equal to 2 such that phi of 2x is less than equal to d into phi x for all x greater than equal to 0. So the following results of order of magnitude of rational Fourier coefficients were obtained by Tan and Zhao. If f is of phi lambda bounded variation, then f at n is of order phi inverse 1 upon summation 1 upon lambda j, where j is from 1 to 2n. And if f is of lambda BVT, then f at n is of order 1 upon summation j equal to 1 to 2 and 1 upon lambda j whole raised to 1 by e. So the generalized variation was defined in 2011. Let f be a complex valued measurable function defined on I, which is equal to AB, lambda be non-decreasing sequence of positive numbers such that summation 1 upon lambda n diverges, and for 1 less than equal to p less than equal to infinity, 1 is less than equal to p and is strictly increasingly tending to p as n tends to infinity, and f belongs to lambda bounded variation if this variation is finite, where Im is a finite collection of non-overlapping subintervals of I, and d lambda pn is defined as in 11, and f of Im is f of bm minus f of an, and delta m is infimum of n minus bm. So if you take f belongs to lambda bounded variation, then f would be bounded function on I. So if we take lambda equal to 1, then the class reduces to Jacobus variation, and if we take phi n equal to 2 raised to n and lambda equal to constant 1, then lambda class reduces to beta n unit as class. So if we take f belongs to lambda bounded variation, where 1 is less than equal to p is less than equal to infinity, and n belongs to z star, then f at n is of order as given in equation 12, where tau n is defined as in equation 30. So sir, here in Fourier coefficient we are not getting this term, and in rational Fourier coefficient we are getting this extra term because it is a general kind of system.
So what is the meaning of 12 when p is equal to infinity?
Yes sir. So basically here in definition, Pn is tending to infinity. That's only we are considering.
No, but the formula, could you look at 12? 12, equation 12. So, there in denominator p is acting.
P is tending to infinity.
No.
P depending on P,
It's depending on Pn. Pn is tending to P, and here P is equal to infinity. So Pn is tending to infinity.
I am looking at the formula 12. You have taken 1 less than equal to p equal to infinity.
Yes.
So how this formula 12 look like if p equal to infinity?
So it would be some sequence which is tending to infinity, right? So we would be getting Pn terms.
No, at infinity what will
At
happen?
infinity,
What will happen?
So for example, let's take Pn equal to n. So it is increasingly tending to infinity. Then here f at n would be p of n. It would be replaced by p of n.
in 12, what is the interpretation when p equal to?
Yes, sir. That's what I am saying. Here if we have Pn tends to p. So I am taking Pn tends to infinity. You are telling me to take p equal to infinity, right?
But when you put p equal to infinity, formula should make sense. No?
So that's f at n at nth term. What is the value of Pn for Pn tending to
Just like
infinity?
in LP space, what is the role of p is less than or equal to infinity? So it's asking that when p is equal to infinity, that what happens with the space? Then it will come to the formula. Same thing.
Yes,
Same thing. So what interpretation you have for LP space, the same interpretation is for the here also.
No, but in LP it is L infinity. It is a different definition. You cannot put p equal to infinity in LP and get L infinity. L infinity is altogether a different definition. So here what is the meaning? Okay,
Sir,
if you do not have answer, you can go first.
Can I try one more time to explain to you? If I am taking here sequence Pn which is increasingly tending to infinity. So
Yes,
the
yes.
sequence is going to
So when
infinity.
you get the supremum,
Yes.
then a space of all bounded functions, then an infinity will exist.
Yes, sir.
You have to do like that.
But this is the estimate of the Fourier coefficients.
So, for example, if you take f at n, we are considering f at n. So here it would be replaced by p of n, right? So there I am taking p of n equal to n, say for example. So it would be replaced by n term.
What I understand is if your Pn goes to
Yes,
infinity,
ma'am.
then you are taking P as infinity. In that minute, he has written
No, but
P as infinity.
here P is different. No? Pn tends to P is okay. So tau n is appearing in
Okay, for this coefficient.
1 upon n is also appearing. N is appearing
That is P of time. P
P
into
of tau.
P of tau.
P
P of tau.
That is function.
It's a
Oh,
function.
so it is p of tau.
It's a function. It's a function.
I thought that it is in multiplication.
Oh, okay, sir.
And infinity should also create the space of all bounded functions.
Yes, yes.
So it is always having the same properties.
Yes,
What
yes.
what LP is having.
Yeah, this is
So it
my misunderstanding.
will convert. Then the question is that whether it will be best approximation or not.
Sir, here we
Have you heard
can't.
about the best approximation? Well, uniformly convergence.
Usually it is not uniformly converted.
Is it so?
Uh,
Will it convert uniformly?
no, sir. In rational Fourier series, we aren't sure about this.
No, I'm asking a question. Can you make it uniformly convergent? Because you have told about the point-wise convergence, na?
Yes, sir.
So, will it converge uniformly like the Fourier series?
So I'm not sure about that.
Nowadays work on
Yes. I have seen your thesis. I did not find that it is uniformly.
Yes, sir. Because
in the literature also, I think nobody has
done the study of
Then for that you should get the best approximation.
yes, sir.
ENF tends to 0, when n tends to infinity.
Yes. So Jacobus defined the following bounded relation. Let f be two periodic measurable function. Let Pn be increasing sequence such that again 1 less than equal to Pn increasingly tending to P for 1 less than equal to P less than equal to infinity. F is of B lambda variation if this variation is finite. So note that if f is of B lambda variation, then f is essentially bounded on P bar.
Actually, sometimes it is creating the confusion when you write P of n.
Yeah, okay.
Okay,
I
so
should have used
when it
different
looks
terms.
like a function,
Yes, sir.
that is why you simply write P, then it will work.
Okay. Yes, sir.
Sometimes it creates confusion.
So if f is of B lambda variation and n belongs to Z star, then f at n is the Fourier given equation 15.
P and in the flow, that notation.
But tau n is defined as an equation 16. So the above result is analogous to rational Fourier coefficient which I obtained for classical Fourier coefficient by Jacobus. Next, for a function f in L1 t bar square, which is supercreating in both the variables, double rational Fourier coefficient double rational Fourier series is defined as in equation 17, where f at mn is mnth rational Fourier coefficient of f given by equation 18. So again, if we take alpha k equal to 0, then our series becomes double Fourier series of f. So if f is integrable function, mn belongs to z square, then f at mn tends to 0 as modulus of mn tends to infinity. The above result can be considered as double level lemma for double rational Fourier series. Let f in LP t bar square p greater than or equal to 1 and beta 1 beta 2 belongs to 0 to 1. Then we say that f belongs to this ellipsis class if omega p of delta gamma is of order delta raised to beta 1, gamma raised to beta plus delta and gamma raised to 0, where omega p of delta is given as in equation 19 and delta f x by h k is given as in equation 20. So the following result was obtained for double rational Fourier coefficient. If we take f in this ellipsis class, then f at mn is of order is given equation 21. Again, if we take alpha k equal to 0, this goes so far rational Fourier series as 0, then we get analogous result for double Fourier coefficients. So the definition of phi lambda bounded variation was extended for two variables, a measurable function f.
Alpha, you included beta is equal to what? P, no. Lip what? What is the result of lip what?
Sir, it would one of the modern
What is the relation between leap one and other classes? you take alpha equal to 1, leave one class.
Leave one.
Equivalent to some other classes or whatever.
I guess this is the additional term, na?
Yes,
One
yes.
upon additional term. It will not come in the Fourier series.
Yes, sir. It's a additional term.
So, is there any conclusion about when you take alpha is equal to 1? Leave 1 is a constant.
Yes, sir. It would be the same result.
Leave one is nothing but the class of functions of bounded
Bounded
variables.
variation. The result would be 1 upon mod plus 1 upon mod plus 1 upon
The
mod.
result should be coincide with the class of functions of bounded variables.
Yes. And so the final result would be the here beta 1 beta 2 is replaced by 1, that is reserved for bounded variation for double Fourier series, double rational Fourier series. So a measurable function f defined on rectangle R2 is said to be a phi lambda bounded variation if this variation is finite, where again phi and lambdas are as previously discussed. J1 and J2 are finite collections of non-overlapping subintervals in I and Kj respectively, and f of I cross j is defined as in equation 20. So the above generalized variation is in sense of Vitali. Here the function did not be bounded and it can be easily verified from the example below. If we take f from 0 1 square to r and define fxy as 24, then we get variation is 0 and it is unbounded, but f belongs to phi lambda bounded variation. So phi lambda bounded variation is given in the sense of RD as follows. If we take f in phi lambda bounded variation such that marginal functions f dot c belongs to phi lambda 1 BD and f a dot belongs to phi lambda 2 BD, then f is said to be of phi lambda star bounded variation. So here if f is of phi lambda star bounded variation, then f is bounded function in R2. And if we take phi x equal to x raised to p, we get lambda BVP, and if we take phi x equal to x, then again we get lambda BV for R2. Note that in the above definition of phi lambda bounded variation, phi lambda star bounded variation, it is typical to impose phi as an n function, and which we will consider from E onwards. The following result is obtained for order of double rational Fourier coefficients. If f is of phi lambda bounded variation and is integrable, then f at m n is of order is given in question 25.
Is it not L2? Term 16? Not L2. Belongs to it.
Yes. And the similar result can be, same result can be obtained for phi lambda star bounded variation. And here if we take phi satisfies delta 2 condition and f belongs to phi lambda star bounded variation, then f at m0 is of order is given in question 27. So the lambda bounded variation is generalized. Lambda bounded variation Pn tends to P. Generalized bounded variation was defined in the sense of Vitali and Hardeep. Let f be a complex valued measurable function on R2. Lambda b as previously defined, and Pn and Qn, Pn b as also previously defined. And the variation on subintervals of I1 and Ij2 of I1 and I2 respectively is given by equation 28, where f of I1 plus I2 is defined as in 29. So we define the term here. If f and b lambda bounded variation is defined earlier, then f belongs to b lambda variation if this variation is finite, where again I1 and Ij2 are finite collections of non-overlapping subintervals of I1 and I2 respectively. And again delta I1 plus I2, I1 and Ij2 is as defined in question 30. So the above definition is in the sense of Vitali, and the definition can be extended in the sense of Hardy as given below. Here simply we have to take the marginal function lambda 1 BD and lambda 2 BD. So note that the function f lambda star BD is again bounded. So if we take f belongs to lambda star bounded variation, 1 less than equal to p less than equal to infinity, mn belongs to z star square, then f at mn is of order is given in question 32 and tab is as previously defined. And if we take f belongs to lambda star BD, 1 less than equal to p less than equal to infinity, then f at m0 is of order is given in question 33. So these are again analogous results to double Fourier coefficients. Let f be in an infinity be duplicated in both the variables. Let Pn and Qn be in increasing sequence such that Pn less than equal to Qn, and again 1 less than equal to Pn increasingly tending to P for 1 less than equal to P less than equal to infinity, and similarly for Qn, then f belongs to b lambda variation if this variation is finite, where again delta fx by xp is given as in equation 35. So if f is of b lambda variation, then f at mn is of order is given equation 36, where again tau n is as previously defined. If marginal function are in d lambda variation, then f at m0 is of order as given in question 37. And again, tau model is previously defined. So if we take alpha k equal to 0, then we get the analogous result for double Fourier coefficients, and the results are extension of equivalence for order of Fourier coefficients. Note that these results are further extended for multiple rational Fourier coefficients. So for any n x belongs to minus pi to pi, the partial sum of rational Fourier series of f is given by equation 38, where again f at k is kth rational Fourier coefficient of f, and the conjugate rational Fourier series is given by equation 39, and the partial sum of conjugate rational Fourier series is given by equation 40. So if we take alpha k equal to 0, then we get conjugate rational Fourier series reduces to conjugate Fourier series.
So conjugate Fourier series is again a Fourier series or not?
Yes, sir. The n would be the whole term minus I into sin k f at n. So we
No,
can,
will it always happen? Conjugate Fourier series always a Fourier series?
I'm not sure.
Because it is the point at why we do separately study conjugate Fourier series when you already study the Fourier series.
I'm not sure.
Then why you separately use the separate to study the conjugate Fourier series?
Then it should be not same.
This is a separate study, na?
Yes, sir.
And you already have taken the Fourier series.
Yes.
So if it will happen that conjugate Fourier series is a Fourier series, then there is no point in studying conjugate Fourier series separately. No?
Yes, sir. But
It is not necessarily a Fourier series. Not necessarily a Fourier. There are some examples also which leads that the conjugate Fourier series is not a Fourier series.
So many science
Science series. So it will convert that. So that is why the separate study may exist.
so in view of tangent points,
इसको होना चाहिए था इसका।
in view of tangent points result for alpha k equal to mod alpha k e raised to I k, and x belongs to minus pi to pi, the partial sum of rational Fourier series of integrable function is given as in question 41, where rational digit kernel is defined as in 42, and theta and px here is given by equation 43.
Because for conjugate Fourier series, when you apply the function spaces, so every function space will not work. Every function space will not work for conjugate. Just like conjugate generalized genuine space. It will not work for conjugate Fourier series. But Fourier space will work. Generalized Fourier space will work.
because of their most of the conjugate Fourier series related results are on the Fourier space.
Fourier space only. So when you will get phi x t is equal to f of x plus t minus f of x minus t.
Yes, sir.
So it will not fit in that particular space. That is the reason.
Okay.
Because it is not necessarily the Fourier series, it will not qualify that space.
In the sequel, we assume that conjugate function is defined as in equation 45 and size given as in 46. So the rate of convergence of rational and conjugate rational Fourier series are obtained as follows by 10 and 20. So if f is a bounded variation is continuous, then modulus of s and fx minus fx satisfies this inequality, and similar inequality for conjugate Fourier series.
It is not necessarily the limit interval function f, your rational function.
So it should be a level interval function. It's a bounded relation, so it would be of level inequality. So if f is a bounded measurable function minus pi to pi is regulated, and then this inequality in 49 is satisfied, where oscillation is given as in supremum mod x x t minus x y, e y belongs to a. And the above result of rate of convergence of rational Fourier series is analogous to the Fourier series result. In view of Waterman's result, from previous theorem we obtained Waterman's analogous result for rational and conjugate rational Fourier series. We suppose that lambda mod k by mod k is non-increasing if for fixed and h of t is continuously non-increasing function minus pi to 0 and 0 to pi such that h of t is equal to lambda mod k by t, where t is a pi by n plus 1, k equal to plus or minus 1, plus or minus 2, plus or minus 3. So if f is of this lambda bounded variation and these two inequalities are satisfied, then we get this 50th inequality. So now if we put lambda equal to 1, h of t equal to 1 by t, a equal to pi by I plus 1, b equal to minus a, then we get result for bounded variation. So it's as previously defined. So if h is a bounded variation, then we get this inequality.
Particularly 1 by t equal to what?
Yes, for h of t equal to 1 by t.
Range of t is the range.
Here we will define the h of t, how it should be. So basically,
Never zero, na?
this result was done by Waterman in Fourier analysis estimation, and then we are basically extending it.
No pole, na?
So for Mn and partial sum of double rational series of integral functions given by 52, and oscillation of function is defined as we already previously discussed. In the oscillation of function h to c over subrectangle a1 given to c1 p1 of ab cross c is defined as in equation 50. So this is two variable analysis. So for following notation and condition will be used in the rest of this chapter. For m in n union 0 we define eta km is equal to k pi by n plus 1 for k 0 1 to m, I km plus s close interval eta km to eta k plus 1 m, and I km minus s minus eta k plus 1 m to minus eta k. So for a function f in t bar square we define s of x y as in 55 and psi as in 56. Note that here f of x plus 0 y plus 0 is limit f of x plus u y plus v u v tends to 0 s and u v greater than 0, and similarly other limits are defined. So if f is bounded measurable function on t bar square, 2 pi we in each variable, then and f is regular, then we get this inequality 57 in terms of oscillation. Now we denote f belongs to variation v2 if f is in lambda star vv, and similarly we denote variation for lambda. Here lambda would be lambda j mu k, and v1 is defined for lambda equal to lambda j variation of ab for the marginal function f dot 0, and similarly v1 f of a is defined for lambda equal to mu k variation on cd of marginal function f0. Here also we assume the same conditions previously defined, and similar condition for g is given. Here lambda mod j by mod j is replaced by mod q, mu mod k by mod k. So if we take f belongs to lambda star bounded variation, f is a continuous function, and this inequality are satisfied, then we get this inequality 60.
Mu means moment.
No, here just we are defining the lambda variation. So again, if we take f in lambda star view, f is continuous, and for mn belongs to n, 61 is satisfied and 62 are satisfied, then we get the inequality 63. Here 80 is defined as in 64, and BT and CPQ are defined as in 65 and 66 respectively. For a greater than 0, we have T of a is close interval 0 to a, and for a less than 0, T of a is close interval a to 0. So in the sequel, we will consider the rational orthogonal system with fixed poles. So here we are considering fixing these poles, and alpha k's are equal to r, and we get this 67 from the rational orthogonal system by considering alpha equal to r. So the rational trigonometric series is defined as in equation 68, where Cn is sequence of complex numbers and x belongs to t. Note that if r is 0, then rational trigonometric series reduces to classical trigonometric series. Stenogenetic define the following variation for sequences. A null sequence of complex number is said to have bounded variation of order m if this inequality is satisfied, that is summation mod delta m cn is finite, where delta m cn is delta m minus 1 cn minus delta m minus 1 cn plus 1, and delta 0 cn is cn. So here if for some m in n a complex sequence cn belongs to vbn, then rational trigonometric series converges pointwise to some function for x belongs to t minus 0 and converges in LPT metric to f for 0 less than t less than 1. If we take r equal to 0, then we get the analogous result for the classical trigonometric series due to Steno-Jevic and Fourier. So the double rational trigonometric series is defined as in equation 69, where Cjk is double sequence of complex numbers where xy belongs to t bar square, and the rectangular partial sum of double rational trigonometric series is defined as in equation 70. So the series is said to converge in Princeton sense if we take as jkxy tends to fxy as minimum, jk tends to infinity. And in addition, row series converges for each fixed value of k, and column series converges for each fixed value of j, then double rational trigonometric series converges regularly to fx. So the following bounded variation of higher order was defined by Chen and Lu. A double sequence of complex number Cjk is said to be a bounded variation of order m if Cjk tends to 0 as modulus maximum of mod jk mod k tends to infinity, and this condition in 72, 71 and 72 are satisfied. Where again delta mn is defined as in equation 74 and 73. In another way we can define delta mn as defined in equation 74. So if for some m in n, double sequence, complex sequence is in VB2M, then the double rational trigonometric series converges regularly to some function fxy for xy belongs to t minus 0 square, and converges in LP T2 matrix to f for n is 0 less than t less than 1 band when minimum jk tends to infinity. So if we take alpha equal to 0, we get the results for double trigonometric series, which are obtained by Core and others, and Morix respectively. And this was obtained for order m, and here it was obtained for order 1. So this is the list of publications. This is
rational Fourier series will have the no poles. Rational Fourier series will have no poles.
Yes, sir. Basically, rational orthogonal system we have poles alpha base.
It will generate orthogonal basis.
Yes, sir. Yes.
So if there is a pole, then the system will be unstable.
Yes.
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 Then your system is stable. When in the rational Fourier series, you do the closure now.
Yes.
You take the open case, then you do the closure also.
Yes.
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 Then it goes the integrates and boundary.
Yes, sir.
Isn't it?
Yes, sir.
So if there is a pole, then the system is unstable. In the control theory, the system should be stable. So if there is a pole, then how can you get the rational Fourier
Sir,
series?
we haven't considered that conditions. In fact, we were trying to do different conditions. Like here, you are telling that
If
second.
compulsorily there is a pole,
Yes.
then it is not at all the will generate the rational Fourier series.
Yes. Yes.
Then work is to generate it out.
Yes.
Yes. What can you do? What is the remedy?
Sir, as of yet, I am also.
Because the control system should be stable.
Okay.
So for stability, you have to take the poles out
Okay.
of the domain. Then what remedy? Direct here.
Sir, I am also not sure as of yet because we are considering these conditions. We are removing the whole select system, and we have done the research on this work only.
That is why I asked sometime that somewhere should be the closure should be included.
Sir, the thing is,
If there is a pole on the boundary,
sir, it is
then what will
difficult to
happen?
prove these results when we include the poles
If
as
there
well.
is a pole on the boundary, then what will happen?
In fact, sir, there are some authors who are trying to do that, and they are considering these inequalities, but they are not able to prove this type of result. They are doing some other kind of results. So my work was.
I guess the simple phenomena is that when you reduce your, the domain, the pole immediately will go outside.
Yes, sir. Yes.
If there is a pole inside the domain, then
Then
you
we should
reduce
reduce
the domain.
Oh, okay.
Then the pole will go outside.
Yes.
So then you can get your required series.
Yes.
But how it will be done? Because when you reduce your domain, then what will happen with the boundary, the domain? That will be a question.
How you are manipulating the alpha
Yes.
here?
That's
So
a
then
like
you
good
get the
It
required
is kind
value.
of 1 upon a lambda minus 1, na? A lambda minus 1 like function. So I think it would be maybe the work.
Yes, sir. I think that would be a good work to study.
Usually we do in C, है ना? कि when the function is actually deliverable to the users, so what they do, they remove the singularity somehow.
Okay.
If they cannot remove it, they
Reduce
reduce.
the domain.
They do it. When you reduce the domain in such a way that the singularity should lie outside.
Okay, sir.
Then ultimately the purpose of series is to use in some applications. है ना? And application is one of the good application is control theory.
Control theory, yes.
So for the control theory, the system should always be stable.
Okay.
When the
Yes, sir.
system is unstable, there is no use. So no rational function theorem. Rational function theorem.
I can't recall.
Okay. So it's ultimately I found it's a very good work, Mr. Vyas, because he got published all SCI papers in a very correct interval of time, 3 years. So work is good. I have done from my side. If you anybody from the all of you can ask the questions if anybody is interested. I already asked many questions. I am satisfied. You as a student, for your curiosity, you can ask because this is a very famous subject of analysis.
Feel free to ask the question
Ah.
if any of you have.
Usually, students feel some anxiety in asking the questions, even in the class.
Be comfortable and ask no problem.
Please.
Every function of bounded variation is level. What about the higher classes? Say lambda dB, phi dB, or in two variables?
No, sir. In fact, we have to define how we are defining the definition of bounded variation, right? In Vitali sense or Hardy sense. So, for example, if we take Hardy sense, then it would be level measurable.
What is Hardy sense?
So, yes, sir. We have
So
already.
can you go to the definition? One at least one.
Okay, one.
Go above 5 dB. So you are taking measurability in the definition.
Yeah, yes, sir. Here we are taking measurability.
So my question is, why you need to take measurability in the definition, and is that every function of bounded variation is level. Now how far you can go and achieving measurability? We are generalizing the concept of bounded variation. So phi dB, lambda dB, and many more. Right? So how far we can go with the measurability? We want to achieve measurability from the from condition of function being of generalized bounded variation. So how far? Now here you are considering this measurability in the definition itself.
If I remove that and then
without a measurability definition, can you achieve measurability from the definition of function of bounded variation? That is in simply, suppose you have function of bounded variation, you do not include measurability in the definition.
we are not doing that. Yes, sir.
So here also it is an expectation that the function is in some sense of bounded variation.
Yes, sir. So we should not be including the definition, but try to prove it that it's measurable in some sense.
For example, for lambda dB, you must be aware of some results. Do you know whether you get measurability automatically?
I'm not aware. For two variables.
No, single variable. See, for a function of bounded variation, it is a difference of two increasing functions.
Yes, sir.
So discontinuity will be countable in only number. So set of discontinuities is 0.
Yes, sir.
And function is already bounded, and therefore it is Riemann integrable, so level integrable. So that is the proof. Now, when you go to lambda b, just lambda.
If x plus and minus 1 would be existing, it would be
Yes,
counted.
yes.
So it would be measurable.
So again, right and left hand derivative exists at every
Yes.
point. So discontinuity will be only of the first kind.
Yes.
So countable will mean number, and So you can go up to that.
Okay, yes. I got your
So
point,
now
yes, sir.
up to which stage we can go
For double.
for achieving measurability from condition of being of bounded variation in some space.
So that I'm not sure. I would look into it.
Okay. And
Any other question before? Please. Any other question from new business students?
ફીલ ફ્રી કઈ હોય ડાઉટ હોય તો પૂછી લો, ગભરાવાની ચિંતા ના કરો, પૂછો ફીલ ફ્રી. હા
so sir has actually asked somewhere why not in L2, L1. Can you go to that there? So I think the reason may be this only.
Okay.
Here.
હાર્ડી સ્પેસ હોય ને એટલું હોય કે હાર્ડી સ્પેસ હોય બાઉન્ડેડ
Why to include? Why not only condition 5 lambda VVG2?
Okay, yes, sir.
And why?
હાર્ડી સ્પેસ
Sir is saying that
Yes,
you don't have to
exactly.
do measurable and we don't want this condition.
That is
Directly
what-
only this
that is
condition.
what I am telling. That when you consider only one class, it
Yes,
need
sir.
not be measurable.
Yes, sir.
So because it is in L1, you will get measurability.
Measurability.
Now it is bounded also.
Yes, sir.
So it will be then in there.
Yes, sir.
But I guess in his case he cannot leave the measurability.
રાઈટ.
He cannot leave the measurability. He is compelled to consider the measurability.
Yes, sir.
Otherwise he cannot get the convenience.
Yes, sir. That's why.
Even the function will be unbounded also.
No, he cannot leave the measurability. Because when the function will not be measurable, then he cannot use the space.
Yes, yes.
Can I say something? No, you come to
Sir, can I take a moment? Thank
Yes, please.
Sir, I would like to thank first of all the department, all the people, faculty members, teaching, non-teaching staff for helping me throughout this PhD journey. I would like to thank everybody, external experts, sir, and the man who was present, PhD council member for coming over. Thank you, sir, for coming. Sir, I would like to especially thank you, Vyas sir, for helping me throughout this journey. And I would like to especially thank Yogesh sir and Sayajirao ma'am for helping me with this seminar. Thank you so much. And Papa, thank you. આજે આવવા માટે. Thank you.
So I guess he now concluded the things, and from my side I have done. So he has done the work very beautifully. As I already told that in a very short span of time of 3 years, he got published 6 SCI or SCI expanded papers in journals. So I guess he deserved to get the PhD degree. God bless you.
So, all the teachers, please come and help for some kind of snacks.
Congratulations.
Congratulations.